Okay, guys, this is the exam that I prepared 2 years ago. And due to distant learning, I hope you do not treat that like an exam and don't stress out. Just do that, do the exam like a homework, like a in-class assignment, and get somewhere comfortable and quiet and start working on it. The exam that I prepared in 2018 has 5 questions on it, and it also came with a formula sheet. You may use that formula sheet, or you can just go through your notes, be prepared, or you can prepare formula sheets for yourself. This year the formula sheets will not be provided because, well, it's an open book exam. So, and I prepare formula sheets for you on on a midterm already. You may reuse that. It's very useful. Okay, let's begin with question one. Question one is very actually question one is the same question that we have gone through in our midterm exam. Basically, when you have something like that, divide the whole problem into 3 portions. Okay, element 1, element 2, and element 3. The stiffness matrix are the same. Okay, EA over L all the time. Okay, and then you just only the force factor is a bit tricky. Okay, for the first and second portion, you have to do integration to get the force factor. Anyways, I have already gone through that for our midterm exam solution. Just review it, please. You can hopefully feel comfortable with it. Now, question 2 is a bit more interesting. What do you see there? It's a bridge with a column. So right away, you know what? I'm so nice right here. I already defined the notes for you. Notes 1, notes 2, note 3, and notes 4. So right away, you understand there are right away you understand there are 2 beam elements, one longer, one shorter, and then I have a column as well, which is a spring or rod elements. So we name them 1, 2, note 3, and note 4. Okay, now we rewrite the boundary condition. This one is 2,000 pounds. Okay, and because the bridge is a symmetric, right? So I gonna rewrite the weight of the truck as 5,000 pounds because everything splits by the column, right? Okay. Now let's answer the question one at a time. Okay, I provide a lot of guidance here. What is the total length of the bridge in inches? Well, as the total length is 250 feet, right? 250 feet times inches per feet. $3,000 inches. Okay, and because this is 3,000 inches, that portion right there is gonna be 1,000 and the shorter portion is 500 inch. You okay so far? Any chats for me? Okay, great. I'll carry on. Okay, determine the local stiffness matrix between nodes 1 and 2. I is 10 inch to the 4. E is 3. E, okay, that's not too tricky. Okay, now you take up the formula for the beam elements. Okay, I believe it's a times I, which is a 100. Okay, divide by length cube, 1000 inch, so 1e3 cube. Okay, and then I look at the formula. So 12 6e3 negative 12 6e3 well, that term is the same. 6e3 2e6 4e6 3 times this 3 that becomes 30. Is that right? Now 3 times 3e 10 10. So 3e10 3e10 and then 1e3 to the cube, so it's 9 10. Yeah, that's right, 30. Okay, guys, are you with me so far? See, easy. I got part A right and part B right. Okay, the next question is C. Determine the applied force contributed astro between nodes 1 and 2. Oh yeah, that's right. It is there's a astro applied to it. 1 pound per inch. So force vector. Oh, by the way, I should name it. This is element 1. Force acting on element 1. Okay, so which is negative 1 times what's the force vector? I forgot. Force vector for the weight. Okay, weight L over 2. So weight is a negative 1 inch. Okay, guys, remember the sign is so important. Eh? Negative 1 times weight times length is a 1000 inch by 2. The second term will be negative 1 times length squared. Okay, again, negative 1 times. So 1e to the 3 squared to 1e to the 6 by 2. And then it will be e to the 3 divided by 2. And then finally, oh, this is positive, times 1e to the 6 divided by 12. Sorry, I missed a 1 here. Okay, when you deal with finite elements problem, right, you got to be very details oriented, you know, do not skip any sign, you know what, and also worst thing to do is nervous. Do not be nervous, calm down and attack the problem one at a time. 500 negative 1e6, negative 500, and then plus. Okay, you may express the term like that, or you can, it's up to you, you can calculate it. You know, what is 1e to 6 divided by 12? And okay, let me use my calculator. Okay, negative 83.33 e to the 3. Okay, any questions so far? All right, part D. Determine the local matrix between nodes 2 and 3. What is the difference between nodes 1 and 2 and 2 and 3? The materials are the same. The only difference is they're shorter. So K2 equal to 300 to this. No, sorry. 8 times 1 to this area. And then the length will be 500 divided by, divided by 500. Okay. Anyways, I'll calculate that later. 12, 6, 3, so it's now 3 into 3, 12, 3, 3. Negative 3. Okay, done. Another question is done. Right here. This is let me check. Okay, now let's the next part. Determine the applied force between nodes 2 and 3. We'll deal with F2 now. Negative 1 times 500 divided by 2. Okay, negative 1 times 500 squared divided by 12. And then negative 1 times 500 divided by 2. And positive 500 squared divided by 12. Okay, done. Okay, determine the local stiffness matrix of the center support. Okay, this one is tricky. Ideally, okay, the K3, okay, is A E over L, and then 1, 1, negative 1, negative 1. Because it is a symmetric problem. So that's why we divide by 2, okay? Because the column is split by two model. So A is a 20, G is a 3E5. Yeah, that's right, 3E5 right here. And then the length is, how high is the column? Oh, the column is 25 feet. 25 times 12. And then divide by 2. Split it. So it is 1E4. Perfect. Now we have all the ingredients. Let's cook the dish. Wow, what a mess. Okay. Set up the global matrix. Now, the first step, I would like to define the global displacement vector, because that displacement vector will drive me to assemble. Okay, basically, the global displacement vector will define the location where you put the entry of the matrix, to the new location. Okay, anyways, first step, 1, 2, 3, 4, we'll just name it as is, okay? So let's put it this way. Okay, so V1, and then phi 1, okay? Right here, 2, so V2, phi 2. And 3 will be V3, phi 3. And then note 4, it only moves along the rod element, and that rod element is vertical, so it is V4. So now let's recap. The first element looks after these 4 values, degrees of freedom. The second element looks after these 4 entries. And then the third element, the rod element, just looks after, oops, interesting. Guys, any questions so far? All right, so I'll carry on that, okay? So I name them 1, 2, 3, 4. It's gonna be a 7 by 7 matrix, okay? Now let's move back. The location for elements 3 will be 5 and 7. Now, the location for the second one, second element, right, will be 3, 4, 5, 6. Okay. Those little circle numbers are very helpful. It's gonna tell you where you put that numbers into the new global matrix. Okay, so if you do that often, you may skip that, but I found it very helpful if I write it down, so I know where to put the values for element 1, 1, 2, 3, 4, and then 1, 2, 3, 4. Okay, done. Now let's start with the force vector. The force vector, the first portion of it, right here. Okay. Negative 500, and then 83.33. Negative 83.33 equals B minus 500 again, plus 83.33 Okay, we look after, this is the first force vector, or the force applied by the, or the weight applied by the astral. Okay, now the second element, shorter thing, so it's negative 250. Negative 250. Okay, this is negative 20. Negative 250. And then okay. Okay, for note 1, okay, there's a force attaching the beam, and also there's a moment holding the beam in place. So we say plus F1 plus M1. Okay, and then note 2, there's a force acting on the note 2 by the lamp pole, which is a negative 2000. Negative, always remember the note 2000. And then note 3 right here, negative 5000 acting on the V3. So finally, there's a reaction force acting on force note 4, that's pushing everything up. Okay, that's my force vector. Global matrix. Okay, you just copy this mass. Okay, no, I'm not gonna copy it here. I don't want to. If I really do this, it takes me another half an hour or so. This is going to be right here. It's a K1. Okay, for the K2 is right here. K2. Okay, guys, there's one thing you must pay attention to. When you do addition like that, right? Make sure you already time this scalar factor into the box. Do not let it hang outside, because if they have K1 and K2, they have very different scale factor. Okay, the K outside the bracket is different. You cannot just add it at the box like this. You have to multiply everything inside, then you add it together. And same as K3, okay? You multiply that value inside the box. Then you can add it 1e4. So right here, so the displacement small. One got a code. Okay, V1 by 1, V2 by 2, V3 by 3, V4. And then the last matrix, it goes to right here. Yep, that's right. 1e4, negative 1e4, negative 1e4, and 1e4. Okay, finally, my favorite part is to apply the boundary condition. This is 0, this is 0, V2, phi 2, no, there's something there. And V3, yes, it goes down for sure. However, because of the symmetry, there's no turning in node 4. And finally, V4 is a locked-in type. So you're down with 3 values, okay? And you just multiply that to the center. So you get 3 equations and 3 unknowns. And how much does the truck sink? You just solve for V2. V2 is how much does the truck sink? Okay. If you don't have that value calculated, if all the steps are right, you get 85% already. You know, if all the assumption boundary conditions good, and if, I would suggest, during the final exam, right? Once you're here, do not solve it. Go to the next problem. Okay. When you have some time, you come back here and do the mathematics or geometry, whatever, algebra, and calculate V2. So, any problem?
I have a question.
Yeah, what is it?
So when it says how much does the truck sink and you use V2, why V2 and not V3? Where
I am sorry. No, sorry. It should be V3. Yes.
okay.
My fault. Yeah. V2 tells you how much the lamppost sink. Okay. Yeah, that's right. V3 is how much. I'm confused. Yeah. So, any questions?